Welcome to the statistics lecture on March 30th. Today we're going to be doing section 10.1. This is tests involving paired differences using dependent samples. In my book, this is page 406. I'm not sure if it's the same in yours. Many statistical applications use paired data samples to draw conclusions about the difference between two population means. Data pairs occur very naturally in before and after situations, where the same object or item is measured both before and after a treatment. So, we have a definition for what dependent samples means. The formal one is two samples are dependent if each data value in one sample can be paired in a meaningful way with a corresponding data value in another sample. What that basically means is we are taking the same object and we are making measurements under two different circumstances. And hopefully we will see that and it'll make more sense in a minute when we do example 2. We are using the same methods that we've been using, which is hypothesis testing. We've been doing hypothesis testing for the past few chapters and lessons. Now we're just doing it again, where this time we are measuring the difference in two data sets. So previously, this chapter we're going to be using exclusively the student's t-distribution. Previously, that looked like t was equal to some x bar, a standard, minus mu. That was our mean of our data set, remember? And that's divided by the sample standard deviation, further divided by the square root of the sample set. We're using this equation again to find our t-test statistic. It's going to change a little bit though. So now we are going to have a d bar term replacing x bar minus a mu d term, and that's divided by an sd term divided further by the square root of n. So what do these mean? D1 is the difference of two data sets. Mu d, well, I didn't write that down, but it's the population mean of the difference of our data sets, and we'll see what that means mathematically in a bit. And then SD is also a new thing, SD, and that is the standard deviation of distances. And I misspoke earlier, just plain D is the difference of two data sets. So I'm gonna take this, can I drag it over here? I don't know how to use this thing. That's regular D. D bar is the mean of the differences. And that wording might be confusing to you. We're going to see what that practically means here in a second, mean of differences. Okay, so those are the new terms. Quickly, previously you were typically given your value of like the sample standard deviation and mu. Now you're being asked to calculate it. You've been taught how to do that before, but I'm going to do it again. I'm going to cut to a video later on my calculator showing you how to do it on that device, and hopefully it's close enough to what you own to figure it out yourself. Sometimes you're given values of mu d and sd, but we're going to learn how to do it ourselves as well. It can be done manually without a calculator, and that looks like sample standard deviation of the data set can be calculated with the sum of the difference of two data sets minus the mean of the differences squared over the sample size minus 1. This calculation is very tedious to do by hand, which is why learning how to do it on a calculator or finding an online calculator to do it with is very important. Okay, let's go to example 2, and let's do this, because the process is very much the same. We're changing a couple of variables, we're changing how they look, but it's what we've already done, so don't worry. I'm gonna clear the board. So, example 2, page 409 in my book. A team of heart surgeons at St. Anne's Hospital knows that many patients who undergo corrective heart surgery have a dangerous buildup of anxiety before their scheduled operations. The staff psychiatrist at the hospital has started a new counseling program intended to reduce this anxiety. A test of anxiety is given to patients who know they must undergo heart surgery. Then each patient participates in a series of counseling sessions with the staff psychiatrist. At the end of the counseling sessions, each patient is retested to determine anxiety level. Table 10.2 on the next page indicates the results for a random sample of 9 patients. Higher scores means higher levels of anxiety. From the given data, can we conclude that the counseling sessions reduce anxiety? And we're going to be using a 0.01 level of significance. Before we answer this question, let us notice 2 important points. One, we have a random sample of 9 patients. That means random samples hint to using the student's t-distribution. And we also have a pair of measurements taken on the same patient before and after the counseling sessions. Now remember, since we are using dependent pairs, we have the same object measured at 2 different intervals. So we have pairs of measurements, same patient. We can tell this data is dependent. These data sets are dependent on each other. In our problem, we can count the sample size N is equal to 9 pairs, which means 9 patients. And the D values are found in the 4th column of table 10.2. I have reproduced table 10.2 right here. So what this is these are the measurements of, I believe B is after. No, B is before counseling. So I'm going to do before and after. This is their, it might be heart rate, I don't know. It's their measure of anxiety before counseling per patient, and this is the after. What's important to us, we want to calculate our D values, which is easy. All we take is B, the before, minus A, the after, to create column 4. Let's see. So let's begin with A. In A, we are going to we're going to determine the null hypothesis and alternate hypothesis, as well as state the level of significance. So we are told in the problem statement, this is A, that the level of significance alpha is 0.01. And the hypothesis that is being defended, or we want to test the claim that the counseling sessions reduce anxiety. This means that the anxiety level before counseling is expected to be higher than the anxiety level after counseling. So what we're testing is B minus A, before minus after, and we're seeing that if before minus after is higher. So our hypothesis would be, hypothesis would be H naught mu D equals 0. The null hypothesis is always no change, so mu D will always equal 0. And then we're testing if the mean difference, the average, basically, the mean of all of these data points is increasing. That's going to tell us if our therapy sessions are helping or not. So our alternate hypothesis, H1, is going to be mu D greater than 0. So that's part A. In part B, we are going to, if we can assume that D has a normal distribution or simply has a mound-shaped symmetric distribution, then okay, basically we're trying to determine the D bar, the mean of the differences, the standard deviation of the differences, and the test statistic. Oops. So D bar is just going to be the average of all of these values. We can calculate that by hand. We can also do that by calculator. I'm just going to give it to you. Our D bar is equal to 33.33. Our sample standard deviation is a little bit harder to find. It would require either the equation given before or the calculator. I'm going to give it to you and show you how to calculate it later. It's going to be 22.92. Okay. Now that we have these values, we can calculate a test statistic T. So our T test statistic is going to equal D bar minus mu D over sample standard deviation D divided by the square root of N, exactly what I gave you before. D bar was 33.33. Our null hypothesis was 0, so we're going to subtract 0. Our sample standard deviation was 22.92, and our sample size was 9. Okay. When we calculate that, our T statistic is going to be 4.363. Okay, now for part C, we want to find the p-value so that we can compare it to our level of significance. So let's start on a part C down here. I'm gonna cover up some of this. For it, we're going to need the table in the appendix, and I have that pulled up. That table is table 4 in the appendix, and I have it here. Okay, so if our T statistic is 4.363, first we wanted to find our degree of freedom. It's calculated the same. Our degrees of freedom is going to be the sample size minus 1. That gives us a degree of freedom of 8. And now we are going to find the interval that our T value falls into. So for 4.36, our T value is going to fall into between 3.3 and 4.5. So if we go up here, we know that our test was one-tailed because we're trying to find a mu d greater than 0. We're only looking at one tail. That means our p-value is between 0.005 and 0.001. So we're going to take that back. We're going to say that p is between 0.001 and 0.005. I just went to look to at the table you're given in the book. We don't have quite a precise range here, so in your book, all we have is an interval between 0.005 and 0.0005. So the example answer is this right here. So it's not as precise, but it's okay because it's going to accomplish what we need it to accomplish. Now we can take this value for p. We don't have an exact value. A calculator would give us an exact value. We don't have it. But it is enough information to conclude the test. So part D, we're going to conclude it. We know that if the p-value is less than alpha, we reject the null. The greatest that our p-value can be is 0.005. So p is equal to 0.005. This is a good deal smaller than our alpha value of 0.01. So that means we can reject the null hypothesis. So what this tells us is at a 1% level of significance, we conclude that the counseling sessions reduce the average anxiety level of patients about to undergo corrective heart surgery. Now we're going to do example 3, using the critical region method to conclude our test rather than comparing our p-value to the alpha value, which is pretty much just using a more visual method than a more math method. So example 3 uses guided exercise 2 values, and we learn in guided exercise 2 that well, we're trying to determine if giving educational toys to children will lower the age that they begin to read at. We're seeing if it helps them develop faster. In that test, we determined that H0, the mean was 0, because it always is, and that our null hypothesis is that, and that our alternate hypothesis is there any change at all? So we could just test to see if the reading age is decreasing, but this test is just going to see if it changes at all. If there's any change in how early children start to read. So we're testing that mu does not equal 0, which makes this a two-tailed test. From the previous problem, we calculated that d bar was equal to negative 2.33. Our SD was 2.16, and then we calculated our t-statistic with those and found that it was negative 2.642. With that t-statistic, we want to find out, we're going to use the critical region method to see if the null hypothesis is rejected. So if you remember the critical region method, is taking the bell curve and marking where our t values lie, and then determining if our level of significance is inside or outside of the boundaries that we mark. Since this is a two-tailed test, we know that we're going to have markings on both sides. This corresponds to a negative 2.642 t value. Since it's two-tailed, we also have the equal and opposite 2.642 t on this side. Now we need to determine where our level of significance falls. So our level of significance is 0.05. Let's find a t value that corresponds to that. So we go over here to our table. Now I realize the table that you have in your book is going to look a little bit different, but we're going to get to the same answer. We have a two-tailed test, so we're going to use this second range right here, and we're going to pick this right here because this 0.05 is our level of significance. We know from the guided exercise that our sample size is 6. That means we have a degree freedom of 5. So we're going to go down until we hit degree freedom of 5. That gives us a t value, our level of significance t value of 2.571. So that's roughly right here, 2.571. We can shade in our important areas. Now what this tells us, what this sketch tells us, is that our level of significance is outside of the critical region. The shaded area on the two sides of our calculated t statistic is the critical region, t critical. And in this region, H naught is rejected. Outside of the region, H naught is accepted. Or otherwise, it's not rejected. We do not reject the null hypothesis. Since we see that our level of significance is here in the middle, we do not reject the null hypothesis. So in words, that would simply be at a 5% level of significance, educational toys do seem to make a difference in reading age. And that this conclusion is consistent with guided exercise 2 if you had done it. Now I am going to cut to a camera recording of my calculator showing you how to put the data sets in and how to get these values on a calculator rather than doing it by hand. So get ready for a jump.
Okay. This video might be kind of shaky. I apologize. I don't have a better setup to use. We're going to learn how to use our calculator. We've done this before. It's going to happen a little bit differently this time. We're going to use our calculator to calculate the mean of the differences and the standard deviation of distances. So, to begin, we're going to go into our statistic menu, and we're going to click on edit, and that's going to open up the list editor. Now, in guided exercise 2, we are given a table of values. So list 1 values are going to be 58, 61, 53, 60, 71, and 62. We're going to have a dependent data set, L2, it's going to be 60, 64, 52, 65, 75, and 63. Now, when we go over to our list 3, which I accidentally deleted earlier, list 4 is going to be the same, we are going to write in the function of list 1 minus list 2. So to get to type in lists on my calculator, I hit second and then find list 1. Now I'm going to subtract list 2 from that, and that's going to generate a new list of values that we're going to use to do calculations. So now that we have that, we can quit out of the list editor mode and we can go back to stat. We're going to go over to tests and down one to t-tests. Now this might be called test on your calculator. I'm not sure. I don't know what calculators you're using. But we're going to click on this t-test right here. We are always going to say that our null hypothesis is 0. And we're going to be accessing list 3. So remember, we're going to hit second function and then click on L3 to pop list 3 in there. We don't need to change the frequency. And now we determine what tail test we're doing. This is the same problem as example 3, basically. We remember that problem 3, example 3 rather, we had a two-tailed test, so we're going to say that the alternate hypothesis mu does not equal 0. Now we're going to calculate it. When we hit this, we're going to be given a lot of really useful information. So it gives us the x bar value, which is the d bar value. So what a setup this is. Our x bar value, we're just gonna write it here because the calculator isn't using the standard variables that the book is using. X bar is going to equal, it's really tough holding the phone in front of your eyes than seeing what's in front of the phone. X bar is equal to d bar. So we can see that d bar that we're going to use for our t-statistic is negative 2.33. You might remember that number is equal to negative 2.33. The SD, which in the calculator is called SX, is 2.16. So over here we're going to write in 2.16. And we could use those to calculate the t-statistic, but it's actually just given to us, negative 2.65. Sorry, negative 2.646 or 645. Either is close enough. 6, 5. Yeah, we'll just keep it like that. And then it's actually already given us a p-value, which we don't need. For example 3, we didn't need it because we use the, what's it called? We use the critical region method, but it might have been useful for guided exercise 2. And it's gone ahead and counted our sample size in for us. So rather than using an online calculator or doing it by hand, which is really painful when it comes to calculating SD, the sample standard deviation, we can do all this within a calculator. If you don't have a calculator capable of this, I'm sure you can find a something online that will allow you to do it. And I believe that's all for the lecture. Normally rather than cutting back to my screen recording, I'm going to give you your homework here. I can just show it, actually. We're going to follow the syllabus, and for chapter 10.1, do problems 1, 3, 4, 5, 7, 9, 12, and 14. I am going to be making a test 8 for you. I never received it, so just going to make it myself and send that out along with this video. So homework 10.1 and test 8 will both be due next Monday, which is April 6th. So have a good week and good luck.